Hello Year 12. Today we're going to carry on with Unit 6, Equilibria, and we're looking at Part C, which is the equilibrium constant Kc, and you may have seen this particular expression as a generalised form for the equilibrium constant, which is what capital K is. In chemistry, when you've got a K, that means constant. In this case, it's Kc because the squared brackets around each species refers to the concentration. Whenever you see a squared bracket around a species, it refers to the concentration. But more on that in a moment. First things first, what do we mean by a homogeneous reaction? We covered this a short time ago, but I'd like to see if you can remember. Just pause the video and think about what do we mean by a homogeneous reaction. A homogeneous reaction is a reaction where all the species have the same physical state. So in other words, you have solid in solids, you have liquid and liquids, gas and gas, or aqueous and aqueous. All of the species in the reaction are in the same state, in the same phase. This is important because we can only use Kc for homogeneous reactions. So whenever you're thinking about Kc, the equilibrium constant, you're thinking exclusively about homogeneous reactions. So here is a very, very simple equilibrium reaction where I have A moles of A and B moles of B reacting to form C moles of C and D moles of D. Equally, because this is a reversible reaction, you can take C moles of C and react them with D moles of D again to decompose the products and turn them back into the reactants. You may also recall that whenever we've had to write any sort of equation based on this, it's always to do with the products divided by the reactants in some way. And this is what Kc is. We're taking the concentrations measured in moles per decimeter cubed of each product multiplied by the number of moles. So this is the concentration of C to the power C, where C here is a number here, and this number here is this number here, referred to in the stoichiometry of the reaction. And you've got D, the concentration of D multiplied by the power of D divided by the concentration of A to the power A, the concentration of B to the power B. This is a generalized way of remembering Kc for this general reaction here. It's the concentration of the products raised to the power of the number of moles divided by the concentration of the reactants raised to the power of the number of moles for each reactant. So here's another equation, same as before, and what we can do is we can think about what Kc means in this context. Well, Kc, if Kc is bang on 1, that means that in this instance, the concentration of the products divided by the concentration of the reactants to their respective powers will be the same. Any number divided by another number, the same number, is always 1. So whenever the Kc is bang on 1, which is highly unlikely and highly rare, the equilibrium will be slap bang in the middle here, right? What this diagram shows here is this diagram shows that the equilibrium constant is much less than 1, right? So in other words, the equilibrium position, the position of the equilibrium is shifted far over to the left-hand side. This links in nicely with our last lesson on Le Chatelier here. So the size of these boxes here represents the relative size of the concentrations. You can probably guess what's coming up next is that where Kc is much greater than 1, then that means that the equilibrium position is shifted heavily over to the right-hand side. The concentrations of the products is far greater than the concentration of the reactants. I'd like to stress what we discussed last time, which is the fact that both of these systems, this bottom system and this top system, are both in equilibrium. It's simply that in this top system, the equilibrium constant is less than 1, and in this bottom reaction, the equilibrium position is far greater than 1. In both instances, the concentrations of the reactants and the products are not changing in time. This simply shows the position of that equilibrium, either lying far over to the left-hand side or lying farther over to the right-hand side. Example then, for a particular reaction in which we can work out Kc, this is a reaction with hydrogen gas, with iodine gas, forming hydrogen iodide. So we've got 2 moles of hydrogen iodide in the same phase as 1 mole of hydrogen and 1 mole of iodine. Pause the video now, guys, and have a go at writing the equilibrium constant Kc for this reaction. Hopefully you got this answer, where Kc will be equal to hydrogen iodide squared, because there are 2 moles of hydrogen iodide over here. Don't forget it's the concentration of hydrogen iodide in squared brackets, divided by the concentration of hydrogen multiplied by the concentration of iodine. Both of these are 1 mole of hydrogen and 1 mole of iodine, so this is the concentration to the first power, which you may as well not write it at all because that's the same as just writing the concentration of hydrogen multiplied by the concentration of iodine. Hopefully you got that answer. Well done if you did. If not, hopefully you can see how you got to this from this equation. Let's look at the units then for this particular situation. So Kc here we've already established will be the concentration of hydrogen iodide squared divided by the concentration of hydrogen multiplied by the concentration of iodine. If we cancel out units for concentration, because all of these are concentrations, then we'll end up with the units for Kc. So if we look at this here, we have the units of concentration are moles per decimeter cubed, but this will be squared. So this is going to be moles per decimeter cubed times by moles per decimeter cubed. Equally on the bottom, we've got moles per decimeter cubed in terms of the concentration of hydrogen multiplied by the concentration moles per decimeter cubed of iodine. Let me change pointers here to a pen, and what we're going to need to do is we're going to need to cancel out, right, some of these, because remember that anything divided by itself is 1 and we can cancel it. So pause the video and see if you can work out what will be the units for Kc in this particular case. Hopefully what you can see, guys, is that because this is squared here, this means there's moles per decimeter cubed times by moles per decimeter cubed on the top. So that means that 1 moles per decimeter cubed is going to cancel on the top and on the bottom, but another is going to cancel on the bottom as well. So in other words, Kc in this instance will not have any units. It's dimensionless. There are no units for Kc because all of the units will cancel out in this particular instance, meaning that for hydrogen iodide, the formation of hydrogen iodide, there is no unit for Kc. This won't always be the case, as we'll see. You're going to need to work out the units for Kc on an individual case-by-case basis. Here's another example then. So this is the reaction between ethanoic acid, CH3COH, and ethanol to form this guy over here and water. What type of reaction is this? First of all, you should have come across this reaction before in organic chemistry. And what's the expression for Kc? Pause the video, guys, and give it a go. If you've worked out the type of reaction and the expression for Kc, let's also see if you can work out the units for Kc based on your expression for Kc. Pause the video and give that a go, and then we'll run through the answers. Alright, so you know hopefully that the reaction is an esterification reaction, and Kc will be the concentration of ethyl ethanoate, this is ethyl ethanoate, an ester, multiplied by the concentration of water, the other product, divided by the concentration of ethanoic acid, multiplied by the concentration of ethanol. The units for Kc then are pretty much the same as in the previous case, because if I switch to a pen here, this will be moles per decimeter cubed divided by moles per decimeter cubed, which will cancel out. The concentration of water is also in moles per decimeter cubed divided by the concentration of ethanol in moles per decimeter cubed. So all of the units cancel out. It is dimensionless, just as for the case for hydrogen iodide. All of the units cancel out. Kc in this instance has no units. Okay, so hopefully that all makes sense. Let's cover one more question on this, which is the reaction, the decomposition of PCl5, phosphorus pentachloride, forming phosphorus trichloride and chlorine gas. This is a homogeneous reaction. All of the reagents are in the gas phase. See if you can work out the expression for Kc, and subsequent to that, see if you can deduce the units for Kc. Pause the video and give it a go. Hopefully you worked out that Kc will be the concentrations of the products, which are both 1 mole of each, so it's just going to be the concentration of phosphorus trichloride multiplied by the concentration of chlorine, divided by the concentration of the reactant, which is phosphorus pentachloride, right? The concentration of phosphorus pentachloride. Here, though, in terms of the units will cancel like this. Because you've got moles per decimeter cubed times by moles per decimeter cubed on the top, that one of those will cancel out by the moles per decimeter cubed of the phosphorus pentachloride on the bottom, meaning that the overall unit, what you've got left, is moles per decimeter cubed. So the units for Kc in this instance will simply be moles per decimeter cubed. Okay, the next thing that we're going to cover is slightly more difficult, quite a bit more difficult actually. We need to find the value of Kc, and to do this we need to do this by experiment. We need to know, first of all, the Kc expression, and we'll need to know the concentrations of each species. So the most straightforward way to calculate this is to put the concentrations into a Kc expression, to multiply it out, to simply calculate the answer, taking care with the unit, of course. And as you know, Year 12, I've gone on about this from day one. It's really, really important that all the way through your calculations you show every step of your working, including units. This is why, because if you don't do this, you'll make a trivial mistake, a trivial error, which will cost you dearly. The second method is that you might be given the number of moles reacted rather than the concentration. In that instance, it's slightly harder because you have to use this equation, concentration equals moles divided by volume, and then you can just simply use method 1 to work out the value for Kc. I'll let you pause the video just to write a few notes on that, and then we're going to go through a worked example on this. So before we look at our work example, I just want to pause briefly and remind ourselves about why we need to learn about Kc. We've sort of talked about this earlier in the video, but I think it's necessary to just revisit it again to think about what this means. Well, Kc simply tells us where the equilibrium lies, where it is in relation to everything else. So if Kc is exactly equal to 1, then we say the equilibrium's slap bang in the middle. If Kc is greater than 1, then the equilibrium is to the right, to the side of the products. And if Kc is less than 1, the equilibrium is to the left of the towards the reactants. I just wanted to remind you about this before we looked at the worked example so that we can understand what these numbers mean in the context of some real examples. Okay, how does changing the temperature affect Kc? Well, if we think about Le Chatelier's principle, remember that if you make a change, the system will oppose that change. What do you think that will be for an exothermic reaction? And what do you think will happen to the value of Kc for an endothermic reaction? Right? Have a pause of the video and have a little think about it. Hopefully you've worked out that for an exothermic reaction, if you've got an increase in temperature, that will shift the equilibrium to the left, the side of the reactants, and will therefore decrease Kc. The opposite is true for an exothermic reaction though. If you decrease the temperature, then the equilibrium will shift to the right and increase Kc. So you have to be aware that the opposite can be true if you just change out the word increase here for decrease for an exothermic reaction. I'll give you a moment to make a note of that down in your notes now. For an endothermic reaction then, if you increase the temperature for an endothermic reaction, the temperature will shift to the right. The equilibrium will shift to the right to the side of the products, increasing Kc. Bear in mind, just as for an exothermic reaction, if I swap out the word increase here for decrease, then it would be the opposite. So the equilibrium would shift to the left, which would decrease the value of Kc. Again, I'll give you a moment to pause the video to think about this and make some notes. Here's an example then. So here is a table of data which shows the temperature in Kelvin, 500 and 800, and it also shows you a numerical value for Kc for two different reactions, for reaction A and for reaction B. So reaction A at 500 Kelvin, the value of Kc is 5,000. It doesn't give the units for it, but it's sort of irrelevant in this case. But I'd say usually it would give units, or you'd need to be able to work out the units. And for 800, the value of Kc has gone down to 0.3. For reaction B, though, the opposite thing occurs. For reaction B at 500 Kelvin, the value of Kc is 4.5 times 10 to the minus 2. But when you increase the temperature, that value goes up to 2.8 times 10 to the 3. So I'd like you to use this information to predict whether the two reactions A and B are exothermic or endothermic, but also with an explanation. Why have you come to that particular answer? Pause the video now, guys, and let's see if you can work out the correct answers. Right, hopefully you worked out that A is exothermic. That's because the equilibrium shifts left with increasing temperature, as we saw from one of the previous slides. So the value of Kc decreases with increasing temperature. For B, it's endothermic. The equilibrium is going to shift to the right in this instance with increasing temperature. You get a higher value of Kc. Well done if you got that right. If you need to pause the video to amend your notes, please do so. Okay, last little question to think about then, guys. How do pressure, concentration and catalysts affect the value of Kc? Pause the video, have a little think about this and get back to me. The short answer to this is that they don't. Pressure, concentration and catalysts don't affect the value of Kc. Pressure and concentration, if you increase both, the equilibrium will counteract that change, so it doesn't affect the value of Kc. Catalysts also, you know already about catalysts from the previous unit, that catalysts lower the activation energy for a reaction. They don't affect the position of the equilibrium, right? So catalysts actually speed up the forward reaction and the backward reaction by the same amount because they lower the activation energy. What they don't do is they don't affect the position of the equilibrium. The equilibrium for a catalyst won't shift to the right or to the left. They don't affect the position of the equilibrium. Let's take a look at some calculations then. This is a Kc calculation in this first particular example where I've got 1 mole of A reacting with 3 moles of B forming C and D. Equally, there is a reaction between C and D, the products, to reform the reactants. So C and D can react to form A and 3B. The first thing is to look at this and to work out that Kc will indeed have units. The reason why Kc will have units is because you've got a non-equivalent number of moles on both sides. Here we've got 4 moles and here we've got 2 moles. Wherever you have a non-equivalent number of moles on either side of the equation, then Kc will have units. It will only not have units where the total number of moles adds up on both sides. So if this was 2 moles on the left and 2 moles on the right, then you would find that Kc would not have units, but it will have in this instance. That's an important thing to think about as you're working through these calculations, is will Kc have units? But by all means, please do double check as you go through. So let's look at the question, and a question will give us the initial amounts in the question in terms of the number of moles. So in this particular question, we've got 5 moles of A and 4 moles of B. What that system will mean is that initially it won't be at equilibrium. So initially you'll only have 5 moles of A and 4 moles of B, right? There will not be any C and D in the flask, because remember the equilibrium can only exist in a closed system, and in this instance initially when you put in your reactants there will not be any C or D. So what you then need to work out, and this is quite tricky, is you need to work out the equilibrium amount. So that's what EQM stands for. EQM stands for the equilibrium amounts in moles, and again you'd get this from the question. So in the question, you won't know the equilibrium amounts of A and B. It won't tell you that, but we can work them out. It will, however, tell you in the question the amounts of at least one of the products. So in the question, it will tell us that we form 0.82 moles of D, but we don't know at equilibrium how many moles of each of the other species we've got at equilibrium. We're going to need to work it out. So to work it out, you look at the reaction ratio from the initial equation, which will be given to you in the question, or you can work it out from the stoichiometry. So in this particular reaction, you've got 1 mole of A, right? 1 mole of A according to the equation. You've obviously got 3 moles of B, you've got 1 mole of C and 1 mole of D. Hopefully you can see that from this equation up here. 1 mole of A, 3 moles of B, 1 mole of C, 1 mole of D, as is the case here. So then you need to work out the amount which is being gained, right, in this particular reaction. Well, that's relatively straightforward. There won't be any gained of A and B. If anything, they will have been lost because they will have reacted together to form C and D. But what we do know is that equilibrium, we've got 0.82 moles of D. If we've got 0.82 moles of D, that must mean that we have 0.82 moles of C, because they're on the right-hand side of this equation, right, and they're both in a 1-to-1 molar ratio, right? So we can't say anything about A and B because they're not going to have gained any number of moles. In fact, they will have lost moles because they've reacted together to form C and D. So that will be 0.82 moles of C and 0.82 moles of D, because we're told that in the question and that each of these are in the same molar ratio. The hard thing then is to work out the amount lost in moles, and that will exclusively be for A and B, because C and D have been gained, they haven't been lost. So just at this particular juncture, I'd like you to pause the video for a moment, and I'd like to think about how can we work out the amount lost of A and B using these numbers here. Pause the video, have a think about it, and then we can check your answer in a moment. Hopefully, guys, you'll have worked out that this will have lost 0.82 moles of A, and you'll have lost 3 lots of 0.82 because it's a 1 to 3 molar ratio, right, of B, right? So 3 lots of 0.82. That means that we've got 2.46 because 3 times 0.82 is 2.46. And that we won't have lost any of C and of D, right? We won't have lost any at all of C and D. Well done if you got that. But we still have another further step to do, because whilst that's the amount lost, it doesn't tell us how much that is in total, because we've got to do something with that in relation to these initial amounts. And what we've got to do with that, with those initial amounts, well, first of all, we need to check the ratio. So that should be 1 to 3 to 1 to 1. But we need to work out the, finally, the equilibrium amounts. So I've just cleared this table up a little bit here from the previous slide. So we've now got the amount that's lost of each of A and B, and we've also got the amount gained of C and of D. So to work out the equilibrium amounts, we need to take this number here, the amount lost, away from the original. So that's going to be 5.00 take away 0.82, because 0.82 moles of A has been lost to convert to C and D. So that works out at 4.18. Equally, for B, we need to take the 2.46, the 3 lots of the 0.82, away from the original 4. So that's 4 take away 2.46, which works out to being 1.54. And these won't change because these haven't lost any, they're gained. So that's just going to be 0.82 and 0.82. And from these numbers, we can then work out the value for Kc. However, we need to be careful because we're going to need to divide these by the volume, because this is simply the number of moles, and you'll recall in terms of Kc, Kc is a concentration, right? The C in Kc stands for concentration, and concentration is the number of moles divided by the volume. So we need to take each of these numbers here and divide them through by a volume in order to work out Kc. So let's do that. Kc does have units, so the concentrations must be calculated. You could use shorthand here, where Kc doesn't have units, there would be no need to work out the concentrations. You wouldn't need to take into consideration the volume because it would cancel out. However, in this instance, it won't cancel out because I've got here on this side of the equation, I've got 4 moles in total, and on this side, I've got 2 moles in total. So Kc will have units, and therefore we're going to need to think about the concentrations. So the equilibrium, we can work out the Kc by taking into consideration that the concentration is the number of moles divided by the volume. It needs to be, the units need to be in moles per decimetre cubed. So let's say that for the sake of the argument that we used a half a decimetre cube flask, a 500 centimetre cube flask for this particular reaction, in which case we need to divide each number by 0.5. So we can go through and divide each of the numbers above by 0.5. So for A, that's going to be 8.36 moles per decimetre cubed. For B, that's going to be 3.08 moles per decimetre cubed. And for C and D, both at C and D will be 1.64. So C will be 1.64 and D will be 1.64 moles per decimetre cubed, dividing 0.82 by 0.5. which is also, as I said, 1.64. So the last step is to work out what that means in terms of Kc. Well, we take the numbers that we previously worked out, which we can incorporate into the expression for Kc, which is going to be C multiplied by D, the concentration of C multiplied by the concentration of D, divided by the concentration of A multiplied by the concentration of B to the third power, because there's 3 moles of B. So Kc then, plugging in those numbers, is going to be 1.64 moles per decimeter cubed multiplied by 1.64 moles per decimeter cubed divided by 8.36 moles per decimeter cubed multiplied by 3.08 moles per decimeter cubed, because there are 3 moles of B in the initial equation. When we do that, and hopefully you can do this yourself by plugging the numbers into your calculator, hopefully you can work out that Kc will have a value of 1.1 times 10 to the minus 2. I'd like you to pause the video and plug those numbers into your calculator to verify that, but also I'd like you to work out the units of Kc, bearing in mind that whenever you see a squared bracket, that means moles per decimeter cubed. But take care with this one, because it's going to be moles per decimeter cubed. Pause the video and give it a go. Tell me the units after you've verified that this is the correct answer on your calculator. Hopefully you worked out that it's going to be moles to the minus 2, decimeters to the 6. And here's where I'm going to get my pen out and show that to you, or do my best to. So on the top here, we've got moles per decimeter cubed, and you'll have to forgive me, I'm not the quickest of writing with this particular pen, multiplied by moles per decimeter cubed. Moles per decimeter cubed, divided by moles per decimeter cubed, multiplied by moles per decimeter cubed, to the third power. So one of these will cancel straight away very, very easily. Moles per decimeter cubed divided by moles per decimeter cubed cancel. However, only one of these here will cancel, so really we can write that to the 2. So that's the same as writing moles per decimeter cubed to the second power. And when we do that, we end up with moles squared, decimeters minus 3 times by 2 is minus 6. The problem is that that's on the bottom here. And when we move it up to the top, we change the indices. So because this is, if I can just erase some of this here, just a moment. Let me pull up the eraser. I think hopefully we're okay to see where we got to that particular point. That's the same as having 1 over mole squared decimeters to the minus 6, and that's the same as moles to the minus 2 decimeters to the 6. So we invert the powers because it's an inversion. It's 1 over, it's a reciprocal, it's the inverse of what we actually want. So that is the answer. Hopefully that makes sense. If it doesn't, please do send me a little message through Teams or an email, and indeed we will have some practice at this year 12. I know this is hard, but please don't panic about this, because we'll have practice, we'll get you there. Okay, in summary, I'd like to think about 3 bullet points on what you've learned in this particular video lesson. Once you've done that, I'd like you to make sure that you update your unit guide, particularly the what, how section, as well as the checklist. And remember that what you need to improve, as well as how you will improve, is really important. Those of you who I've recently marked unit guides for will know that I'm most displeased with how well students are engaging with that particular section. To my mind, the what, how section is the most important part of the whole unit guide. So please take some time to complete that rigorously. What some people find helpful is to fill in the little checklist first. Because if there are any areas you're not very confident on or don't feel you know, that will feed into the what, how section. And even if you think you are top dog in all of these particular areas of the specification, you can still state that in your what, how section. So that's really important for me and it's important for you. But there's always things that we can be doing to work on. Right? And remember, for the past paper section, you can, once that is complete, you can mark it yourself by looking at the mark scheme on the VLE. What I will do, Year 12, is I will set some questions for you to be looking at over the Easter period, and it's really important that you do have a well-earned break. It's been very stressful and very complicated this year because of having to close early because of the coronavirus outbreak. I really encourage you to take some time to relax and to recuperate, but I am going to set some questions on this, and we will sort of have a follow-up video lesson where I'll run through the answers to those, and then I will set you the end of unit test for Equilibria digitally. I won't do what I did last time, which is to take them in and mark them, because it's rather laborious having to try and get them back to you digitally. But what I will do is I'll set you the work to complete that, and then I will trust you to self-mark it vigorously, right? Being open and honest, and then communicate to me your score so that I can update my spreadsheet and so that you can see, you can track your progress. I hope that all makes sense, Year 12. If there are any problems at all, please don't hesitate to get in touch with me, and I'll see you next time. Have a good one.